So in this talk, my goal, because Isaac is a very vast topic, my goal is to first give you some sense of how we actually sense weather using normal radars. What is the context of Isaac in sensing weather, and what are some emerging applications in this area? And if time allows, we'll also look into some of the more theoretical work that we have done in signal processing in this particular area, but I'll start from more applied connections. So here's a little bit about myself. You can also read it online. I only want to emphasize that apart from my role at ARL, I'm also a technical advisor of these two very promising startups. First is Hertzwell, which is an automotive radar startup. It is based in Singapore. It is actually Asia's first automotive radar startup. It was launched in 2018, and I've been their technical advisor since then. Second is Aura Intelligence Systems, which is based in Boston. It's a 5G imaging radar startup. That means their objective is to use 5G or communications, wireless communication signals for sensing and imaging. And that topic is very much related to what we are going to discuss today. My primary area of research is radar, and I explore its connections with theoretical signal processing, electromagnetics, remote sensing, and wireless communications. I would like to acknowledge a number of my collaborators whose our joint research is going to feature in this talk today. They are all listed here from University of Luxembourg and Rice University, as well as DevCom Army Research Lab and the US National Academies, which have funded my research for the past few years. Now, in my talk, especially for students, I like to put snippets from my favorite science fiction TV shows and movies where the characters are talking about radar. You will see this throughout the presentation. That is just to keep you more engaged if anything else is not interesting to you in this presentation. But the snippet that you see on this slide is very much related to the concept we are going to discuss today, that is Isaac. This scene is from a very popular Apple TV Plus show, For All Mankind. And for people who may not know about this TV show, it is about a bunch of NASA scientists, and it is set in an alternative fictional historical timeline in 1960s. And in this scene, these two scientists, they are discussing the effect of solar flares because of heightened sunspot activities in early 1960s on communications receivers. So apparently, this kind of radiation has potential to jam communications receivers. Indeed, if you look into the scientific literature of early 1960s, there used to be an IEEE journal, IEEE Transactions on RF Interference, and a number of papers that were published in that journal around that time, they were about exactly this problem, effect of solar flares on communications receivers. Here is a representative paper from that journal. And this is in 1960s. Today, we are discussing Isaac a lot more. At that time, there wasn't so much awareness around this concept. There was a little bit of activity, but not a whole lot. And this kind of solar flare-induced jamming of receivers led to some major diplomatic incidents as well. You can see a headline here from Wired magazine, which says that this massive solar storm, it almost sparked a nuclear war because communications receivers in US were jammed around that time because of this solar flare. And there was suspicion that it was a hostile activity by Soviet Union. So what we are going to do today is we'll explore this concept a little bit more, and we'll also look into that this kind of interference need not always be malicious or bad for either sensing or communications. It could also be exploited for the benefit of both commercial as well as civil applications. But before that, we'll look into some fundamentals of how do we sense weather. For people who may not be familiar with weather sensing, they may find this discussion useful. So we'll look into that. We'll also examine what are the shortcomings of sensing weather as of today. After that, a little bit more about Isaac, and which particular area of Isaac this rainfall estimation is related to. And then we'll explore two particular use cases. One is precipitation estimation using communication satellite signals, and second is precipitation estimation using commercial base stations, 5G base stations, and how it could be useful. And if time permits, we'll look into a more theoretical signal processing application of Isaac as well. All right, so how do we typically sense weather? For that, we need to understand the shape of raindrops, because sensing of weather is fundamentally related to that shape. As you can see from this image that is going to come up, that raindrops, they are not teardrop shape, as you see in paintings or some cartoons. It is an oblate shape spheroid. That means its horizontal dimension is larger than its vertical dimension. So if this particular shape is fundamental to sensing weather, because you can exploit this shape in differentiating raindrops from other scatterers that may be present in the atmosphere. Now, if I have this kind of shape, then polarimetry that Paul had spoken about yesterday, polarimetry could help in differentiating weather from non-weather echoes. And how does that work? For that, assume that we have only one polarization. So for people who may not be familiar with this, an electromagnetic wave is characterized by its amplitude, frequency, and state of polarization. And when radar emits that signal toward a target of interest, and that wave then interacts with the target of interest and comes back, then changes in all these three characteristics, they help us determine the nature of the target. So the time it takes from the transmitter to the target to receiver, that is directly proportional to the range of that target with respect to the radar. Change in frequency is directly proportional to the radial or Doppler velocity of the target. And then we come to this third characteristic, which is polarization, how it can help in differentiating raindrops. So in a conventional weather radar, only one polarization is used, usually horizontal. But now, in most of the weather radars, state-of-the-art weather radars, they are using two polarizations. So in a dual polarization weather radar, it exploits this oblate structure of the raindrop, that is horizontal dimension larger than the vertical dimension. So that's what dual polarization radar can do. And the outputs that you get from dual polarized weather radars, there are several such observables. I have listed some of them here. So for example, the reflectivity, which is proportional or related to the power scattered per unit volume from the raindrops, that can tell us about how much rain is present in a particular resolution cell. So you can get both ZH and ZV. We typically use ZH because that is a much larger quantity to characterize the backscatter. Because there is one raindrop, it's difficult to measure Doppler velocity of just one raindrop in a resolution cell. You will have millions of raindrops. So we don't have a concept of just Doppler velocity here. We'll have a mean Doppler velocity. That is an average of Doppler velocities of all those raindrops in that resolution volume. And then spectrum width as well, because these raindrops, they are randomly scattered within that particular resolution cell. You will get a spread in the distribution of Doppler velocity. Usually the Doppler spectrum is Gaussian shape, so you characterize it with any Gaussian shape, you could characterize it with the first order and the second order moment. First order is the mean Doppler velocity, and second order is the standard deviation or spectrum width. Those standard moments you can get with single pole weather radar, but if you use dual pole, then you get some additional moments as well. For example, differential reflectivity, which is the difference between ZH and ZV, and it can tell us about the size of hydrometeors. Because more oblate it is, you will have much larger ZDR. It will tell you that the raindrops are much larger and so on. Then rho HV, which is a correlation coefficient, usually it is unity for raindrops and non-unity for non-rain hydrometeors, for example, hail. And we have some other parameters like differential propagation phase or PDP, which tells us the intensity of rainfall. So if you get all of this information, obviously, and if you use it properly with certain rainfall estimation algorithms, you can get a very accurate rainfall rate estimation using weather radars. So dual pole weather radars, they are built for this purpose. They provide very accurate rainfall rate estimation. And they come in various flavors, weather radars. So they operate in pretty much all parts of microwave spectrum from S-band all the way to W-band. So obviously, at lower transmit frequency, signal attenuation is very low. And this is S-band weather radar is what is used in US National Weather Service. In other countries, Canada, Europe, India, China, Australia, usually it is a C-band weather radar. So S-band, very low signal attenuation. C-band, there is some signal attenuation, you need to correct for it. But at lower frequencies, the antenna size is also very large. Usually these are very expensive systems and also not portable. So if you want to deploy only S-band weather radars, you will have very few weather radars to cover a particular area. But if you have X-band weather radars for certain regions, it may be more economical to use X-band weather radars. They may also be mobile, small size, and so on. Of course, the signal attenuation will be very high, and its maximum range would also decrease compared to C-band or S-band. And then as we keep on going higher and higher, especially the space-borne weather radars, usually it is KUK band, they are small antennas. You can also sense some very small particles very well at higher frequencies. So at W band, usually they are only cloud radars. Very small particles could be measured, but the range is also very small, just a few kilometers compared to some hundreds of kilometers at S band. Let's look into what are the current shortcomings of this coverage of weather using these kind of systems. So if you look into the US National Weather Service installations of S-band radars, there are about 160 such weather radars in NEXRAD. That's the network of US National Weather Service. And you can see they cover pretty much the entire area of the lower 48 states in the US. And then similar such networks exist in other countries for C-band radar. Now, theoretically, the coverage is almost full using this kind of network. But in practice, there are a lot of gaps. For example, if you just look at S-band weather radar, then you can see even though its theoretical range is about 200 kilometers, sometimes 250 kilometers, that's what NEXRAD shows. But after 80 kilometers or so, the lowest elevation beam is already touching the top of the clouds. And most of the interesting activity for rainfall estimation, that happens in lower troposphere. So if the lowest elevation beam after 80 kilometers is looking at the top of the cloud, we cannot capture some of these other activities, even though the theoretical maximum range of weather radar, this kind of weather radar, is 250 kilometers. In practice, you're only getting 80 kilometers coverage. And then and some other events, for example, tornado, they are almost always lower troposphere events. There's literally nothing to observe at larger heights in those kind of events. At least when it is raining, we may be interested in phenomena such as bright band formation, which may happen at higher heights, even though it may not contribute in rainfall estimation. But for tornadoes, there is not much to observe at larger heights. And then similar shortcomings, they exist for C-band, except that then it is not 80 kilometers. This kind of thing can happen at a much shorter range, with X-band even shorter, and so on. So how can we address these kind of practical gaps in the coverage? That is one of the research questions that we have been exploring for past few years. Now, one simple way could be that you add more weather radars to the network, but then it increases the cost, and there are also issues with interference from one radar to another. Another way could be, okay, let's not do C-band, let's not do S-band, but let's put a lot of X-band radars. But then again, you will have to put thousands of such radars, these X-band radars, to cover for these kind of gaps. So it's very impractical to rely only on radars for sensing of weather on a large scale. Could we use some other sensors? What are our options? So before radar became very popular, we had rain gauges. So rain gauges, they are in situ instruments. They are only looking up. They are very accurate in rainfall estimation. But the problem with rain gauge is that it doesn't provide us spatial coverage. A radar is scanning, so you are getting spatial coverage, very accurate spatial coverage. Rain gauge gives a very accurate temporal coverage, but has literally zero spatial coverage. Often when we are validating rainfall estimates from radars, we use rain gauge as a benchmark, almost as a ground truth at a particular point to characterize the accuracy of rainfall estimates that we get from radars. But there is no spatial coverage, as I mentioned. And then we have some other sensors. For example, if you have a satellite, so I already mentioned about these weather radar satellites, but they are very few space-borne weather radars. On the other hand, communication satellites, they are very large in number. We have hundreds of such communication satellites. So the signal is coming from the satellite, passing through the atmosphere, and then getting intercepted at the ground terminals. And these ground terminals are also very large in number. So the question is, can we use this signal? Because as signal propagates through rain medium, it loses its strength as it is interacting with rain scatterers. That's what we call as signal attenuation. Can we use the amount of attenuation the signal suffers to quantify the quantity of rain that is present in the path of that signal? That's one of the interesting questions to look into. And then we have all these communications base stations, communication towers, which are transmitting communication signals from point A to point B, and which are also going through attenuation as it passes through rain. Can we use those signals to quantify the rainfall that is present, especially in areas where there is a gap in coverage from weather radar? So this is the question that takes us towards this concept of ISAC. We'll look into that a little bit more in a moment. Another motivation to this is that so far, I'm only talking about countries which have weather radar networks, but there are gaps there. There are a lot of parts of the world, especially in developing economies, where there are no weather radars, but the cellular communication coverage is very high. So in those countries, could we use the cellular communication signals to quantify the rainfall? So that is another motivation to look into this particular problem. Now, we have looked into weather radars from S-band all the way to W-band, as I described before. So that is established. But what are some other opportunities within the spectrum for these other types of signals from wireless communications that we could look into? So automotive radar is now ubiquitous, almost ubiquitous in many countries, and that operates at 77 gigahertz. That's a millimeter wave part of the spectrum, but for a very short range, few hundred meters. So that could also provide another input to rainfall estimation for short range. Indeed, there are some companies which have integrated rainfall estimation in another receive processing channel in the automotive radar that they have installed in their vehicles. So that's one more opportunity. And then I mentioned the satellite passive sensing, communication satellite sensing. So active would be a space-borne weather radar, which are few in numbers. And then other types of Wi-Fi signals, which operate again at 60 gigahertz. Some of them are in this so-called FR3 part of the spectrum, which is very close to IEEE X-band for radar. So there are all of these opportunities that are available to exploit and then fill this coverage in rainfall estimation. So obviously that would require integration of this sensing functionality with existing communications network. And that's what we call it as ISAC, which is a very rapidly growing topic of research amongst multiple communities. It has a lot of other applications apart from rainfall estimation. I'll give a glimpse of some of those applications later. But how this topic has developed, why it has become very popular now, let's look into that aspect a little bit more. So I had mentioned earlier about these solar flares and how they can cause jamming of communications receivers. And that aspect has been known right from 1980s. There's something called Dellinger effect, which says that radiations, these kind of solar flare radiations, they can cause fading out of communication signals. So that aspect was explored a lot in 1930s. And then during World War II, there were these radar systems, that very initial radar systems, like Wurzburg system, they also experienced interference from communication. So this problem has been happening right from the invention of radar, essentially, interference from communications to radar or vice versa. Now, how can we avoid this kind of interference if there are two sensors which are operating in the same part of the spectrum? One intuitive way could be that you combine their functionalities. Use a multifunctional hardware that can do both. It can act as a radar as well as communications. In other words, integrate sensing and communications, or ISAC. That's the term people are using nowadays. And if we look into this particular concept of combining functionalities, the very first paper could be traced back also to early 1960s by Mealy, which explains the use of a radar waveform in which you can embed communications symbols. And then in late 1970s, NASA explored this concept further for their space shuttle program, because anything that you're launching in space, it should be compact size, should consume less power, should be very efficient in terms of weight and so on. And one way could be to have ISAC, where you can use just one hardware that does multiple things. So they explored this around that time. And then in 1990s, we saw some work on software-defined radio, which has a capability of sensing the spectrum, and wherever there is no interference, it can transmit in other parts of the spectrum. It was in early 2000 that this concept that we could use unused parts of the spectrum for some other applications gained some foothold. So around that time, FCC allowed the TV white space, so they call it Wi-Fi, those unused frequencies of TV channels to be used for military purposes. And in mid-1980s also, there was some work where FOPEN radar, that is foliage penetration radar, which operates in UHF, VHF frequency bands, it used to encounter a lot of interference from TV and broadcast stations, because they also operate in that same part of the frequency. And a lot of literature in mid-1980s that we see is about interference from those stations on radar. So these interference concepts, they have been explored for a very long time, but it is only in past 10 to 12 years that we have seen an explosion of research in ISAC. So we'll look into why this is happening, why people are looking into it more recently, and why it is more challenging and interesting. You can also think of ISAC as a synthetic aperture, but in a very general concept, not like SAR. Synthetic aperture in the sense that you can get an enhanced performance for sensing by using two different sensors. You can use a radar and communications, and because a communication signal may also get scattered off a potential target, and you can combine that backscatter with radar backscatter to enhance detection and estimation. So in a very general way, ISAC is actually a type of synthetic aperture because we are using multiple sensors. Typically, bandwidth is shared between these sensors, but what we exploit is space and time. You can use different antennas. For example, radar can have its own set of antennas. Communication base station is separately located using a different type of antenna. So you exploit space, you exploit difference in the transmission, and then combine them at the receiver to gain better sensing performance. So that's why this concept of ISAC is very much related to the concept of synthetic apertures. All right, I mentioned earlier that this topic has become more prominent only recently, even though RFI studies, radio frequency interference studies, have been around for many decades. Why that is the case? This because if you take a radar system, it needs wider bandwidth for better range resolution. So wider the transmit bandwidth, higher will be the resolution. In communications, if you take the Shannon's capacity formula, which you may have studied in your communications theory class, so as per that Shannon's capacity formula, wider the bandwidth of the communications system, higher will be the capacity or higher will be the data rate. And now we are going towards 5G and 6G, where companies, they are promising very high data rates, and you indeed need those very high data rates to support some futuristic gaming and infotainment applications. It has become very important for wireless communications systems to have very wide bandwidth. So both radar and communications, they need wide bandwidth, but bandwidth or spectrum is a scarce natural resource. We have only so much bandwidth, and we cannot allocate that to just one application or to one service provider. As you can see from the table on this slide, pretty much every IEEE radar band today has some coexisting communication service, and this problem is only becoming worse as new radar applications come up, for example, automotive radar, or new communications protocols are proposed for some futuristic applications. In fact, so if you see from this graphic on the bottom that I've taken from Ericsson's white paper published in 2022, currently the 5G spectrum range is all sub 6 gigahertz, which is a very crowded part of the spectrum and also very expensive part of the spectrum as well. And it is so crowded that it cannot offer extremely wide bandwidth for all these other applications that I mentioned to both radar as well as communication systems. The only way forward is that you move higher in the spectrum, millimeter wave or the so-called low terahertz band, where depending on which country you are in, you can have access to anywhere from 4 to 15 gigahertz of contiguous bandwidth. And in some cases, it is also unlicensed right now, especially in low terahertz band. So automotive radar, that's the reason why they operate in millimeter wave band, or there are some systems in low terahertz band because you gain 4 to 7 gigahertz of bandwidth in 77 gigahertz part of the band, and that gives a very good range resolution for automotive sensing purposes. And same for millimeter wave communications, you can get very high data rate. Now, communication service providers, they have been asking for this very high data rate for decades, so very high wide bandwidth for decades. As you can see from some of these headlines I've taken from the New York Times, right from 1980s, there has been a demand for more bandwidth allocation to wireless communications. And now with new players entering the industry, these demands, they have become very loud nowadays, and there's a lot of contest between different companies that's going on to access wider bandwidth. And I've put this another headline here. I've blurred the name of the vendor, but you guys can guess it, which vendor I'm talking about, which has refused to rely on automotive radars and relies only on cameras for automotive sensing for the self-driving car. But if you rely only on cameras, you cannot get a very accurate estimate of your surroundings. You cannot measure Doppler velocity very well. And that's why that's another motivation to move towards automotive radar, which becomes feasible only with very wide bandwidth. All right, now, of course, automotive sensing and 5G, those are immediate drivers of growth behind ISEC research. But what about other applications? How serious is this problem of spectrum congestion? And is there anything good that can come out of this? So in general, this problem is very serious. It has both legal as well as interdisciplinary implications. There have been a lot of court cases in US on this spectrum conflict or interference conflict. So I put some headlines here. There was one court case that happened in 2021 when FCC, that is Federal Communications Commission, decided to allocate slivers of sub-6 gigahertz band. So sub-6 gigahertz is very crowded part of the spectrum. They decided to allocate it to unlicensed users. As a result, AT&T decided to sue FCC with the contention that this kind of allocation to unlicensed users would decrease the quality of service they provide to their 5G clients. Another court case was in 2022 when FAA, that is Federal Aviation Authority, that's the agency that deals with airlines, regulations, airports, and so on, asked Verizon, which is another wireless communications service provider, to stop transmitting their 5G frequencies around the airports because it was interfering with this one device that aircraft use for landing and takeoff, that is a C-band altimeter. That led to another court case because Verizon had paid billions of dollars to gain rights to transmit in that part of the spectrum. And then there have been some more recent court cases, especially around the GPS frequencies that some companies, they are trying to acquire terrestrial communications rights to, for example, Ligado and Light Square. And more recently, you would have heard about the dispute that FCC is having with SpaceX and Blue Origin on allocation of certain frequencies for their communication satellites. Now, apparently jammed the entire internet of New Zealand because they were transmitting in that same frequency that New Zealand uses for their Wi-Fi and internet. And just in January 2026, you might have read this headline that a lot of Greek flights, they were grounded because there was interference, communications-induced interference in their ATC radar. So you can see this conflict of spectrum and interference, it is actually becoming even life-threatening nowadays. So recognizing all of this, about 12 years ago, DARPA, which is a defense funding agency, launched this program called SSPARC, whose objective was to develop spectrum sharing technologies between S-band military radars and S-band military communications. And following the success of SSPARC program, National Science Foundation has launched a number of such programs. Some of them are listed here, PAR, SWIFT, NERDS, and so on, to expand this investigation across all frequencies about interference, what kind of interference may be there and how we can resolve it, and sometimes also exploit it for some nice applications. So now that we have looked into the context of this research, that it is taking in the context of all this interference from radar to comms and vice versa, let's very quickly look into what kind of solutions have been developed so far. So if I have to very broadly classify ISAC topologies based on only sharing of hardware, here is one such classification from our very popular paper that appeared in IEEE Signal Processing magazine. So depending on whether the transmitter or receiver or both are shared or not between radar and communications, you get these 4 different types of classes. Figure A is the case when neither the transmitter nor the receiver is common between radar and communications. In that case, both radar and communications, they transmit independent of each other. They don't coordinate with each other at all. Obviously, there is going to be interference at the receiver. In this particular case, which we also called as spectral coexistence ISAC, most of the innovation is devoted on the receive side in the digital domain, where we develop new signal processing algorithms to mitigate mutual interference. So this is very good for legacy systems which have been deployed in very large numbers, and it will cost a lot to change the entire hardware. So in this case, you largely work on the software side and try to reduce this interference problem. Everything else where some hardware is common is called spectral co-design. A very general version is figure D, where I've taken an example from the automotive ISAC scenario. So here you have this red car, which is a common transmitter. It is transmitting a radar waveform with communication symbols embedded in it. That waveform then interacts with other cars in the surroundings, like the blue car and the yellow car. And when it is reflected off from those cars, it is intercepted by a common receiver, which is deployed on the gray car. And the goal of signal processing is twofold for that common receiver. First, it has to extract useful parameters of the targets, that is the blue car and the yellow car, their location, Doppler velocity, and so on. And the second task is to decode the message that was sent by the red car, because it is also a communications receiver. So it's a very challenging problem. If there is some time, I'll talk a little bit more about it. How do we address it after rainfall estimation, obviously. So this is a very general type of spectral co-design system. We also call it bistatic ISAC, because transmitter and receiver, they are not on the same platforms. As I mentioned earlier, this is a very broad classification, and you may ask that if it has been 10 to 15 years since the launch of Spark and there are only these 4 topologies, people must have solved this problem by now. But it's a very broad classification. If you take some other criterion, you will arrive at a different type of Isaac topology, and some of them are listed here. So based on sharing of hardware, we saw how you can classify them. You can have the same waveform for both radar and communications, or a different waveform. It may be the same waveform, but shared on time slot basis rather than being transmitted simultaneously. Then based on the location of transmitter and receiver, you can get different types of Isaac. We saw one example of bistatic. You can make it multi-static. It may also be networked and so on. Generally in Isaac, our objective is to optimize the performance of radar and communications equally. But there can be some cases where you may be interested in primarily optimizing the performance of radar while accepting some degradation in the performance of communications. Those solutions are called radar-centric. Vice versa, you get communication-centric solutions. Today, we are going to focus on opportunistic Isaac, which is different from radar-centric and communication-centric. So in opportunistic Isaac, we don't change the hardware. We use the existing infrastructure of one functionality, let's say communications base stations, and with minimal change in hardware and largely working only on the software, we repurpose it for the other functionality, that is use communications base stations as a radar. So that is called opportunistic Isaac, and which also demonstrates that all these interference issues that we have seen in the past, it may not necessarily be a bad thing, because if your communications station can act as a radar, then you don't have to deploy an additional radar, and it can provide some sensing performance for free because you did not have to make any changes there. So that's what is opportunistic Isaac, which is how this rainfall estimation is connected to this broader area of Isaac. And then there are so many different types of Isaac that are coming up, each with its own sub-community. Sometimes depending on which part of the spectrum you are working, you get different types of Isaac functionality. So about 15 different IEEE societies, they have published literature on Isaac or have a task group which is looking into Isaac, including GRSS, IFT committee, technical committee, FARS. They all are interested in this Isaac concept. And even non-IEEE societies like AGU, AMS, RC, Radio Science Union, all of them have some interest in this Isaac concept. So it shows that how popular this area has become, especially for students. I mean, there are papers that come out almost every hour on Isaac nowadays. 10 years ago, when we started this, we used to see one paper in 6 months. But now I get emails from Google Scholar Alert multiple times in a day that here is a new paper on Isaac. So it's a very popular topic. All right, so that brings us to this first use case, which is satellite communications aided weather sensing. So earlier I had explained about the gaps in weather radar coverage and global gaps because of lack of weather radars as well. So we started working this one European telecommunications company. I'm not supposed to divulge its name because of proprietary reasons. And they approached us with this problem that they have this millimeter wave communication satellites. And as I mentioned earlier, the signal is coming from the satellite, passing through the rain medium, and getting intercepted at the user terminals. And these, unlike weather radars, which are very few in numbers, these terminals, they are about 300,000 in Europe and 2 million worldwide. And all of them are intercepting the same signal. So those are a lot of terminals. And they are present even in regions where there are no weather radars. So clearly we are getting some information about weather in these terminals. Can we use this attenuation that I described earlier and quantify the amount of rainfall present in the path of that signal? So it's a very interesting proposition because of all other reasons that I mentioned earlier. The question is, how do we go about it? If you recall, weather radars, especially dual pole weather radars, they used to get all of these other observables, ZDR, FDP, ρHV, the dual pole moments. Even for a single pole weather radar, apart from reflectivity, at least you get some Doppler information, mean velocity and the spectrum width, and all of that is useful in estimating rainfall. But here all we have is the attenuation data. So how can we use just this one variable? Because we know the power transmitted from the satellite and we know the power received. So we can calculate attenuation. How do we use just attenuation for very accurate rainfall estimation? It's very challenging. Now, if you take ITU's recommendation, they recommend one simple equation because at millimeter wave, there is almost a linear relationship between rainfall rate and specific attenuation. Specific attenuation is the first derivative of attenuation with respect to range. So ITU tells you that R and AH is specific estimation, R is rainfall. They have a linear relationship, which holds true in most of the cases. But whenever the storms become too active, it's not stratiform rain, but it's more convective rain. There is a lot of wind shear. So all these other types of turbulences, when you take that into account, then this linear relationship is no longer valid. If you rely just on that, you will get highly accurate rainfall estimation. So what do we do? So that brings us to the third keyword of the workshop, which is machine learning, right? So in all the presentations these days, there comes a point where the speaker introduces machine learning. This is that point in my presentation, but I promise it is not forced. So we have this information scarce scenario here. We don't know a lot of other observables like a radar does. So we decided to use a deep learning network for rainfall estimation in this case. Now, how do we use it? What we are going to do is we'll train that deep learning network with the nearest weather radar data. And then in the prediction stage, we'll use the satellite link data and to feed to that network and then see what it gives us. So we started this one very toy experiment using LSTM deep learning network because it captures time variations very well. For the southwest region of Germany at the border of Luxembourg and Belgium, so in that box, you see all these black dots, about 25 to 30 user terminals of communication satellites. We decided to do rainfall estimate only in that one box region that you see. Now, for just one terminal, and we trained this network with the nearest German weather service radar, which is called DWD radar in German. It's a C-band radar. So for just one terminal, here are the results. The bottom plot that you see is the instantaneous rain rate. And this is for an event in May 2018. And you can see the instantaneous rain rate of satellite link, which is the red curve, follows that German weather service radar very closely. So it looks like we are getting very accurate estimates. But this is not what meteorologists use. They look into accumulations or cumulative rainfall rate to compare with benchmarks. So when you switch to cumulative rainfall rate comparison, then that is the top plot. And you can see as time elapses, the difference between this deep learning network, the satellite link prediction of rainfall rate, which is the red curve, starts lagging the German weather service radar significantly. And as more time goes by, that difference keeps on increasing. So our goal was to improve this. And I'll show you how do we do that. But let's stick with this boxed region. Let's do this for all the terminals and then try to create a rainfall map and see what we get. So here is one such comparison for a storm that happened in May 2018, that same storm that I was talking about. On the right side, there are two snapshots of this DWD C-band radar observing a storm that is moving towards the northeast. And on the left side is our satellite link, LSTM network prediction. You can see they don't match at all. The LSTM network, it is seeing something with this one blob that is moving toward the northeast, but the intensities, they don't match. It doesn't capture the structure of the storm at all. So clearly for meteorologists, this kind of data is useless. They will just stick with radar. They have no motivation to use our LSTM networks, this fabled output. There's literally no reason for them to switch to satellite link. So how can we improve this? Now, in a deep learning network, if you have more data, you can train your network very well. So earlier we had access to just these 25 to 30 terminals. Then we got access to data from France, about 12,000 such terminals. And we also changed our network from LSTM to a variant of CNN. And with some hyperparameter tuning and some ablation studies, we arrived at a pretty stable network. Here is a result for a storm that happened in May 2021. So left side is what Meteo France C-band radar is seeing, and our CNN-based satellite link prediction is on the right side. And you can see now the intensities, they start matching with each other a lot. And even the structure is captured very well by the satellite link. And bottom two panels that you see, that is the comparison every 3 hours between the Meteo France radar and the satellite link that we have. And again, the structure is captured very well. Now, for Meteo France radar in the Alpine region, they have a lot of blockage. We actually don't even know if the rainfall rate prediction that radar is doing in that region is very accurate, but it does it nonetheless. On the other hand, what we see from our satellite link actually matches the structure of the storm very well, because we have so many communication satellite user terminals in that region, in the Alpine region. So even for that region, you get very good estimate. Then if we have to see, because here it is difficult for me to show how circulation of the storm is captured by our satellite link. So for that, I created a movie. And here again is a comparison, but for a different storm that happened in 2020. So you can see that the satellite link also captures the circulation of the storm very well. It is moving almost in a similar direction as the Meteo France C-band radar. All the black dots that you see on the right side, those are the locations of one of those 12,000 terminals. And sometimes they disappear. Whenever there's an outage in the network, then we don't get any data from that terminal. Despite that, our CNN-based satellite link predictor is able to tell us something about or give us some prediction of the rainfall that may have happened at that point. So this is a very good example of opportunistic ISAC to exploit communications for sensing. And weather sensing is very difficult because we are not sensing a point target. There's a volumetric target. There's a lot of structure that is involved in that. But with a combination of so many user terminals, it's possible to do this. We have done this for Brazil as well. We don't have a very good radar coverage. And Germany also, we have done this. Nowadays, we are looking into Switzerland, which is very difficult to do because of this mountainous terrain. So we have to work with neural network a little bit more for Switzerland. You can also take some of these trained networks and deploy them for those countries where there is no radar coverage. So more like a transfer learning. So you take a trained network, freeze the lower layers, and only the upper layers you update them with the real-time data. So for example, right now we are looking into some Latin American countries where there is not a very good radar coverage, but using a network that was trained on Brazil data. So that is also a possibility here. Second opportunistic ISAC that I wanted to talk about is this was using satellite signals. Can we also use 5G base stations? So there's a difference between sensing using a base station versus a satellite. In the case of satellite, the signal goes through the entire structure of the storm. Here we are only looking in the lower troposphere, so the paths are not the same. You're not going to get very high accuracy in rainfall estimation using 5G base stations, but it can give you at least some input to the rainfall rate algorithm wherever there is a gap in the coverage from weather radar. So this is the work we did with Rice University with Ashutosh Sabarwal's group. And fortunately, Rice University 5G lab has their own base station. They have built their own base station that is deployed on top of the Rice University stadium. So we could do some experiments with that. The idea is to use the full duplex base station. The reason being, if you're going to opportunistically use the base station, usually it is always doing this communications transmission. But there is always a gap, especially if you look into the recent 3GPP protocol, there is a gap where no transmission is happening at the base station. It's a silent period. What we did here is we repurposed that base station to use the silent period for reception. So the signal, the 5G signal that goes for communications transmission, if it is reflected from some hydrometeor, we repurpose that base station to accept or to receive that backscatter in the silent period. And then you process that signal for rainfall rate estimation. So that was the idea. Now, you can do all the modeling. If you look into our paper, I've given the reference at the bottom. So the modeling for weather radar, that is a very well-established topic. Of course, there's a lot of mathematics involved in that. You will find the details in our paper. But you follow the same modeling, except that you have to do it for a full duplex case in this 5G base station. We considered these 4 cases of precipitation sensing. And the differences between this is, in some cases, you may have full knowledge of the clutter in your environment, and you may also know the noise, power, all of those things. In practice, of course, when you are deploying base station from one point to another, you may not know that. But over the time, you may generate a clutter map, and you will have some knowledge of the clutter present. So we did this sensing for both cases, when you know clutter map and when you do not, and we try to compare them. Another difference between these is that either you can use the base stations opportunistically during the silent period, but because this is our own base station, it's an experimental base station, we can also use it intentionally. We can also focus the beam toward a certain direction and try to sense just rainfall and not do any communications functionality. And I'll show you difference between these different cases. So obviously, when you don't know the clutter map, when you're using it opportunistically, this kind of base station, you may not get very accurate rainfall estimate, but you'll get some estimate. And when you know the clutter map and intentionally focus the beam towards the storm, obviously you get much better accuracy in those cases. Okay, so we deployed this base station on top of that stadium. This is our setup. That's the photograph of the base station. And we compared the rainfall estimation for all those 4 cases. So as I mentioned earlier, as expected for case 4, which is the top plot, the estimation error in the channel. So if you get very accurate estimate, the channel estimates are higher, that means better rainfall rate. You can convert it to rainfall rate, for example. So that error is very high for case 4, which is opportunistic sensing without knowledge of the clutter map, because you may be looking at some buildings or some trees. So that will contribute into the errors. But when, if you look at case 1, where we have full knowledge of the environment, we intentionally focus beams toward the storm, then obviously this estimate is very high. And some of our current work is to now compare this with the nearest next red radar. That is not going to look exactly like those communication satellites, because this is very diffuse type of sensing. But nonetheless, as I mentioned earlier, it gives you at least the short range estimate very well. So if you're looking for providing these estimates in a traffic environment for some short ranges, say 1 kilometer or so, this kind of input could be very useful. All right, so those were the 2 cases. How much time do we have? Ten minutes? Okay. So I'll explain some of the other applications we have worked on in the context of this communication signals as well as radar. Now, I come from a military radar background, so obviously we look into the electronic warfare scenario. And if you're following the news, there have been a lot of interesting use cases of ISAC in some of the current events. Here are some headlines, for example. Now, you can use the communication signals opportunistically for weather sensing. You can also use the same type of signals to localize military targets. For example, if you have looked into this news, that Ukraine has successfully used the Starlink signal and passively sensing it without using a radar. Because if they use radar, then they may invite some strikes from the Russian side. So they are using Starlink to localize the Russian tanks in the war scenario, and then using those locations for drone strikes on the Russian tanks. That is another example of ISAC. And in the Iran war, we are seeing this GPS denial environment, or the use of 5G signals to disable the fighter aircraft radars. So that is also happening, use of interference in the electronic warfare scenario. So we also, our most recent work is on what I call as inverse cognition, where we look into the fact that there may be some interference from a hostile entity. We would like to estimate that signal and then try to disable it or try to change our own transmission to escape either detection or disable this kind of a hostile transmission. And that we are looking into what we call this problem as dual blind deconvolution. We have been working on this problem at Army Research Lab for past 3 years. So I don't have time to describe all the mathematics of it today, but just to give you a glimpse what this problem is about. To understand dual blind deconvolution, you have to first look into how deconvolution works in standard radar and communications. In a traditional radar, we transmit the waveform. So we have full knowledge of the waveform. What is not known is the target profile. We can also call it a radar channel. The received signal is the convolution of the radar channel or target profile, which is unknown, with the known transmit waveform. And while looking at this product of this convolution and with the knowledge of the waveform, we try to estimate the unknown target profile. That is the standard deconvolution problem. We know how to solve it using standard radar signal processing. Now consider these kind of cases that I described earlier, where a hostile entity is transmitting a waveform. In that case, you don't know that waveform. And obviously, you don't know the target profile. And you're only looking at the combined product of that convolution. So by just looking at the output, can you estimate both the unknown waveform and the unknown target profile? That is called blind deconvolution. This is for the radar scenario. In communication, similar thing can happen. In communications, it's usually the transmit waveform that is unknown at the receiver, and the channel is estimated a priori. But in these cases where we are talking about vehicular communications and so on, even if you estimate the channel a priori, it may become outdated. That estimate may become outdated very quickly because the mobility is very high. Vehicles are moving, so that estimate may not be very accurate all the time. And you will have this situation of blind deconvolution. In a coexistence receiver, both of these signals, the blind deconvolution of radar, blind deconvolution of communications, will be superimposed on each other. By just looking at the output, can you estimate all four of them? This is what is called dual blind deconvolution. It's a very popular problem in this ISAC scenario, especially from military perspective. To understand this intuitively, imagine two people are talking with each other. You don't know what they said, that is the transmit signals. You don't even know how they sounded, that is the channel information. All you heard is the combined output, and then you are supposed to estimate all four quantities. And because I come from signal processing, so I promise this is the only time you'll see equations in this, but if you come to my signal processing talk, it will be full of equations. But just to give you a flavor of what signal processing in this case entails, so that is the dual blind deconvolution equation that you see on top. So X, both X, they are transmit signals, both H are channels. Subscript R and C, they stand for radar and communications. Asterisk is the convolution operator. All we know is YT, superposition of two convolutions. We are supposed to estimate all four of these convolvents. In general, it is impossible to do so because there are so many combinations of these four convolvents which would map to the same YT. It is what we call as ill-posed problem. But in our recent work, we have shown how you can actually estimate all four of them uniquely through a combination of various signal processing techniques. All right. Some of our other work more recently on this terahertz automotive ISAC. So you recall that blue car, red car problem. So we have done a lot of work on the self-driving cars using combinations of communication signals and radar signals, how you can combine both communications and radar in a single hardware, and then do sensing and communications in automotive area, but using terahertz and millimeter wave signals. In opportunistic Isaac, we also have this interesting application of synergistic imaging and communication. So use communication signals to map the environment, do the imaging. So that's the work I do with this startup, Aura Intelligent Systems. We try to use signals from communication base stations and then try to generate a map of urban environments. It's also a very interesting application of Isaac. Now, there are so many different types of Isaac architectures. I cannot cover all of them. But you can go through all these references that I've provided here, distributed ISAC, intelligent surfaces, drone-based ISAC. This area is very vast. All right, we have come to the end of this talk. Now, at the end of every YouTube video, you have like, share, subscribe, right? Now, this is not a YouTube video, but if you're interested in my research, please feel free to connect with me on my LinkedIn handle, where I frequently post updates about my new papers and upcoming talks. We published this book last year, Wiley IEEE Press, Signal Processing for Joint Radar Communications, and you'll find everything that I described so far, but in much greater detail in that book. You may have guessed I have a lot of interest in weather sensing. Recently, we have published a 3-volume book on advances in weather radar. So it covers a lot more on rainfall estimates using other types of sensors that I didn't cover today. Almost an encyclopedia of advances in weather radar in the past 10 years alone. Last thing that I want to plug in here is that I'm chair of this synthetic aperture radar standard of IEEE, IEEE P3355. If you're interested in contributing to this standard, it is still 1 year away from balloting. Please feel free to reach out to me on LinkedIn, and I'll be happy to engage with you. So with that, I would like to thank you and take up any questions you guys might have.
Anyone have questions?
I hope you like the snippets, if nothing else, okay?
Thank you, sir, for that insightful session. We now move on to another session by Dr. Narayan Rao, sir. So we once again welcome you and invite you to continue the session.
You might have received at least a couple of messages from me in the group. So how many of you are actually ready with your data? Can I see some hands? 1, 2, 3. Oh, it's good amount of them. So, and the second question, you know it, the Python environment, how many of you are able to create it? Not yet? Any issues? Because now I will talk about mostly the data processing. I'll show you a demo, so how to get your own kind of plots, or a quick, the parameters which I have been discussing in the previous talk. So yeah, this is a brief outline of it. So I'll just give a quick. So I thought this would be more interesting to look at the SWIFT technique. So this is how NICER works in kind of more or less geometrical way. So you transmit one pulse and you wait for all the reflections in between the transmission. So for both L band and S band, it can actually operate both frequencies at the same time because you have different frequencies allocation in between. And you might have seen a similar kind of version in Paul's slide. So S band and L band, I've just only kept more relevant towards a polarimetric perspective. So it is capable of operating in single pole, dual pole, compact, and quad pole in both L band and S band. And over India, we get both L and S band, full and quad pole and dual polarimetric modes. And there are different types of products available. You might have already seen this, but I just want to reiterate so this color coding is the first one, mostly is polarimetric products. The RSLCs, GSLC, GCO, so you hear this a lot when you attend any NICER talk. And the second ones are mostly interferometric till this 3, and these are like offset products. And this is mostly derived biophysical or geophysical parameters. And currently availability of open data sets, we have more than 100,000 publicly available. This is what the coverage is. Across the globe, we have at least almost, except northeastern part of India, we have most of India is covered. Same as US. And if anyone, how many of you know H5 files before NICER? HDFI files 1, 2, 3. Oh, a lot of them. So it's good. It makes my life easier to explain. So have you been working with some weather data or something like climate data sets? If you have experience with that, the .nc format, the netcdf format, it's the same thing, similar structure like a hierarchical one. These are called fields. So if you actually look into the metadata in H5 and read into each and every field, there are like more than 320 fields in it. So the entire jargon or the keywords which you have been hearing throughout these talks, like the bandwidths, the frequencies, and what else? The range resolution or azimuth resolution. So you can actually get all of this inside the metadata of a simple the H5 file. Coming to the other mission, the biomass. So similar to the NICER, we again have different levels of products in biomass. The first one is raw data. Mostly it's raw chirps, the time versus the chirp data. And level 1, so these levels indicate the extra steps. So level 0 is like 0 kind of processing, 0 steps. Level 1 is 1 processing step involved. Level 2, 2 processing steps involved from the 0. So for today's, if time possible, if there is a possibility, so we will explore that. Mostly the polarimetric part is mostly we deal with single look complex data sets. This is the current availability of biomass openly available data set over Indian subcontinent, both ascending and descending. One significant difference you can see is the swath width compared to the NICER versus biomass. Here the swath width is somewhat roughly as 50-60 kilometers compared to the 250. That's why even if you have a lot of swaths covered, but not enough area covered geographically. With this brief info of the data availability, so these are kind of a skeleton, what do you call, a basic flow of any pulsar workflow. So you will have a pulsar data, which I've been talking about mostly. It starts with a single look complex data. And then you extract the polarimetric matrix, which we have discussed in the previous lecture, where it is a covariance, full quad pole versus covariance dual pole. Then we do some speckle filtering, though this is kind of optional for some applications, but mostly we do to reduce the speckle, speckle nature or the grainy nature over the spatial grainy nature appearance on the data. Then we generate these polarimetric parameters. Polarimetric parameters again can be entropy, degree of polarization, decomposed powers, and so on. So what we have seen, the basic ones. Then we use these derived parameters, so for analysis or any other downstream applications, whether you use it for a crop mapping or you use it for forest monitoring, or you have n number of applications from this. So, so I'll be talking about the processing or the processing steps, the same steps, which we have implemented in a Python package called Pulsar Tools, which is available both in Python as a Python package and also a QGIS plugin. Though QGIS plugin as of now doesn't have any direct importing functionality as of now, but if you have a already extracted polarimetric matrix, you can actually generate all the descriptors and the plots. I want to give a brief of this package because I've been working since like 6 years. I think I started in 2019-20 during my PhD. So the motivation is something like we have other more popular and what do you call more diverse functionalities available in other polarimetrics SAR processing tools, but we have to adapt to the change in cloud native environment, and also have we need to have to deal with the now petabyte scale data sets. Like you might have seen in my previous slide how I actually process this entire country scale maps. Mostly I've used the same package. So in a way, we have kept it platform independent, so it will work on whether you are using whether Windows, Linux, or a Mac PC. And despite you might have seen, I mean, if you have downloaded the GSLC scene, it is mostly like 20 plus GB, and if you go for a quad pole, it's even bigger than that. So, but how do you actually process that if you have a limited computational resources? So, as Paul mentioned, you can actually read a chunk by chunk or whatever that, like a small piece of the data set instead of dumping the entire data set into your RAM, because memories are limited. Even if you have a 32 gigs of RAM, let us say, and you can load entire 22 GB of data at once, but if you want to process it, and again, you need another 22 GB extra to store the derivative, so which is most of the PCs won't support. So that's why we actually implemented here a chunk-based parallel processing algorithm, so that even an 8 GB PC should be able to handle your nicer data processing. And also you have QGIS plugin for, again, categorized into different polarimetric modes, full or quad pole and compact and dual polarimetric modes. Here is a simple code snippet to achieve those basic steps, which I've shown as a flow chart. So these are the results from simulated nicer data, but this is a kind of basic nicer GSLC code. So you extract a polarimetric matrix, then you generate a quick look image like the false color composite of it. You apply a speckle filter, then you can do a H alpha, the parameters H, anisotropy, and alpha generation. Then you can plot the H alpha plot, and then you can export that to another clustering mechanism. So this is, I mean, it is not even, it is not just limited to NICER or biomass. Currently, it supports more than 10 sensors. I've also extended to Chandrayaan-2 dual frequency SAR if someone is working with Chandrayaan-2 data. So they can also use it and generate, I mean, they can do the polarimetric SAR analysis over Chandrayaan data as well, because there is almost 4 terabytes of Chandrayaan-2 SAR data is available, both north and southern poles of moon. Here are quick numbers of the both Python and QGIS users. So you're not alone if you are starting it. So there are enough people, I would say, are using, though they're not citing. So it's okay. But yeah, even this slide I've kept it so that you see the community. And also another one, I have a request that if you, let us say in few years, you will, once you are kind of more comfortable with SAR and you have your own technique, or if you find any bugs or something, if you want to contribute your own indices, your own technique, because currently it is limited, like we have 100 plus functionalities compared to Pulsar Pro, which has more than 1,000. Because kind of they are also migrating towards Python, because now Python is everywhere. Even if you want to use machine learning over the cloud or Jupyter notebooks, these are kind of more common platforms where one do the research. So here are some of the peer-reviewed papers we published both on QGIS plugin and also the Python package, so that you can kind of rely on this scientific quality of the output. I mean, that's why I kept this slide. So one might think that, okay, it's not kind of a hobby, rather than it's scientifically reliable because people are publishing using this package. So I want to acknowledge some contributions from my supervisors and friends, and also NASA nicer grant when I was a postdoc back in US, and also I've tested this on the NASA ESA collaborative platform called MAP, Multi-Mission Algorithm Analysis Platform. With that, I think with this brief, we can start moving and processing your downloaded NICER data. Any questions so far? Like any difficulties in setting up environment? Because I'll assume that you have set up an environment. I need like the environment is the prerequisite. And if you have a QGIS or any JS software so that just to quickly visualize those outputs or degree of polarization or entropy or any other descriptor you have. Yeah. I think this is what I've shared with you. So just so I want to see like how many of you are successfully kind of ready to process the data, like ready with the notebooks? No? Yes? Or shall I take a WhatsApp poll if you are more introvert like me before? So so that is also fine, because I want to be more interactive if you find any difficulty in processing, because you may not find a lot of support, or when the mission is in pre-calibration stage, it's difficult to find any documentation or support because people are, all the science team is busy in fixing their own and achieving their own targets. So you might have to wait if it is out of this class. So it's up to you. So let's say once you're ready, let me do and follow the same. Oh, it's too small. Let's say. By the way, I use Linux, so you can do an equivalent one in Windows if you have a Conda terminal. I hope this is visible. Even I can increase the size. As you can see, I have the environment YAML file, the configuration file, which I've shared with you in, I think, in the Google Doc, and a GSLC, dual pole GSLC, and a quad pole GSLC, and a dual pole GCO product from NICER. So let me start by creating that environment. Oh. Oh, it's going to take a while. Meanwhile, I have to download these notebooks. It's, GCO. Okay. Oh. Oh. Oh, it is GRSS. Sorry for that. Sorry for that mismatch, but so once you have set up your environment, so you can open your Jupyter notebooks. So how many of you have used Jupyter notebooks before? Oh, that's good. So you know how to use a Jupyter notebook, which is good and makes my life easy. So yeah, now you can see the data sets, the YAML file, and the notebooks. So I'm going to process some GSLC data. So yeah, I mean, if you are kind of starting, so these are instructions how to even set up that environment, how to actually install the package and so on. As of now, you don't need them. And the first block is mostly importing the packages, the classic way of Python way of importing all the required packages for both processing and also plotting. So this is mostly we are using for plotting. So the result, whatever the output, mostly in geotiffs, so we will be displaying. So the second block is nothing to do with the pulsar processing. This is mostly for displaying the outputs as n number of images what you get. So now you can go ahead and change this path of your file, the GSLC. Let me actually clear all the outputs first. I think I should use my mobile's internet, it seems. It's not changing. Sorry for that. Clear all outputs. Let me zoom it. Where is the zoom? That's fast. Yes, for GSLC, to extract the polarimetric matrix, whether it is dual pole or full pole, so we use this function called import NISAT GSLC, which takes a lot of arguments, but the first one is your path to the H5 file and the matrix type on number of azimuth and range looks. This is for the multi-looking and generating second order matrices. Mostly for second or the dual pole matrix, you don't need all of this. You can directly give the H5 and accept the default parameters. And if you want to know more about that function, you can actually click always here. You will get a complete list of parameters and how you can actually use them and what do they mean for full pole and dual pole. So there is a kind of all the functions are well documented, I would say. And if you want to even explore like how many sensors are there, what are the readers and all the source code, you can actually go through this documentation. So as of now, I've kept the path and the matrix type as C2 because it is dual polarimetric data, and 10 by 10 azimuth and range looks. This mostly roughly generates a 100 meter by 100 meter for a faster one. And output format, you can anyways choose from either GeoTIFF or raw binary for backward compatibility with Pulsar Pro and other softwares. And there is an optional cloud optimized GeoTIFF format, and you can build overviews. You can compress the output because GeoTIFFs also support the compression, different compression algorithms. And you can choose a different output directory to store your C2 matrix. So once you have actually set up all these parameters, so now you can choose and run all above. and just to see. So how many of you are able to kind of edit your path to your downloaded files? So how many of you actually run this notebook with your data already? Anyone? One, two. Oh, that's good. Yeah, there is some error, it seems like. What is that error? Now. Oh, I need to change the kernel. So if you face any issue, actually you have to change the kernel here, because different environments you can link with the different Jupyter kernels if you are familiar with that. Otherwise, it will show up here if you have followed the exact same instructions in the document. So it will show up as Pulsar Tools environment. If you select that, then it should be good to run without any errors. So once you have successfully finished the first step, it should create a folder called C2HX, which represents to C covariance matrix 2x2 for horizontal transmission and vertical receive, HH and HV channel. If it is a sentinel data, it would be VB and VH. So yeah, it will take a few minutes based on configuration of your PCs. Yeah, some low-end PCs may take more time, but I assure you that it won't fail. It will generate those outputs. Yeah, at any point of time, if you are facing any difficulty, any error, you can post it in the group directly, or you can ask from there. And once you extract this, you can directly drag and drop into QGIS or any GIS one just for a quick view or make maps. That is fine. So the data set is used, so you can actually calculate it's like 16,512 cross 512 blocks. So yeah, once it is done, you can go and check. There will be a folder created with all your C2 matrix elements, both diagonal and off diagonal elements. Okay. And you can open up any QGIS or ArcGIS, whatever you're using. So how many of you are familiar with QGIS or any GIS-based platforms? Okay, then it's good, because I know I'm kind of assuming that you know that, and I'm just adjusting that symbology. So yes, so this is for the first release of public data. You can also check the geocoding by dropping into a base map. So this is a C11 as of now. Now you can actually see a lot of grainy nature, even if it's a 100-meter resolution, 100-meter pixel size. Now the next step you can do is, if you remember from the flow chart, the speckle filtering. Again, speckle filtering takes a window and the path of this folder and a window size. And the rest of them are again optional parameters. If you are working with cloud optimized geotiffs, you can produce that as well. So how many of you are able to produce a C2 from GSLC? No one? Is it processing? Yes? No? Okay, it's running. I think I should post in WhatsApp poll. Instead, you are too busy in processing the data. So let's see. C2 generation or extraction, I would say. Progress. Yeah, now you can actually vote in the WhatsApp poll. So whether it is in process or already done or you faced any error. So oh, in progress. Okay. 2. Oh, 1 is done. I can see 5 responses. Okay, I can see only 5 responses. 6. Seven. Oh, still in progress. It's good that I haven't seen any errors. No one hit any error. It is good. 11. I think I can just show it here if it works. I can see 12. Okay, I can see one more done. Yeah, it's a huge data set. It may take a little bit of time. Mostly it will take for the mosaicing of all the chunks. Yeah, even if it is the progress bar is completed, it will take time for mosaicing all those 16,000 chunks there. So I want to see at least 5 people finish so that I can move on to the next step. The speckle filtering, I think it's done here, and I've also produced a pseudo RGB. Someone is doing a voice recording? I think I can take some more. Oh, you can have your tea break as well. Are you pros? I mean, you can go through the notebooks. You can already, notebooks are already there with output, so you can see that later also. Oh, it's Manoj. మొత్తం నోట్బుక్ అని చేస్తే సరే జస్ట్ ఎక్స్ట్రాక్షన్ ఇంకా ఒక డిఓపి కావాలన్నా లేకపోతే స్పెకల్ ఫిల్టరింగ్ ఇవన్నీ చేయాలి పర్వాలేదు అందరికీ దిస్ ద ఫస్ట్ స్టెప్ ఎక్స్ట్రాక్టింగ్ పొలోమెట్రిక్ మ్యాట్రిక్స్ then you can do speckle filtering and generate some, yeah, that you can directly, if you generate that also you can directly import into QGIS and see, prepare some maps. Yes.